Okay, in this video we're going to do 3 questions on the pigeonhole principle. The first involving the fundamental counting principle, the second being a geometry example, and the third being a divisibility example. And I think it's important to look at geometry and divisibility because they do pop up not in the new senior textbook, but they do pop up in Cambridge and they pop up in Maths and Focus. So I feel that you should pay particular attention to those 2 examples. Okay, but first example. We've got 30 distinct ties every day, including weekends. He selects a tie. Okay, selects a tie to wear. So he wears a tie every single day. How many successive dates are needed to guarantee? As soon as you see needed to guarantee, you know pigeonhole principle. There is at least one day of the week in which he has worn the same tie on at least 6 occasions. Okay, so let's have a think about what this means. So we want to at least one day of the week in which he's worn the same tie. Okay, so there's a day of the week and there's a tie factor involved. So say on Monday, I could be wearing tie 1. On Monday I could be wearing tie 2. I could go all the way up to Monday wearing tie 30, because there are 30 ties altogether. We could keep going down, 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 and down. And we could form a box here, and we could have Friday, we could be wearing tie 30, Friday, not Friday, last day of the week would be Sunday. Sunday, tie 30, etc., etc. And we're going to imagine all these as boxes. And what we want is we want it to be certain that there will be 1 6 in all these boxes. That's what we want. Okay, because we want to be guaranteed that there's at least one day of the week in which he's worn the same tie on at least 6 occasions. So at least 6 occasions. So remember, the idea is fill out each of these pigeonholes with 5, and then we add one more here, and that will cause it to be 6. So let's have a think. So firstly, we want to know how many, I'll call them tie day pairs. So there are 30 distinct ties and there's 7 days in the week. So there are 210, by the fundamental counting principle, there are 210 tie day pairs that are possible, and they are the pigeonholes. And we want to know how many successive dates. So the actual thing I'm looking at here for pigeons is the successive dates. Okay, successive dates. Then I'll put in bracket the pigeons. So we want to know how many pigeons are required to guarantee that we'll have the same tie day pair for one of these on at least 6 occasions. Okay, so we're going to fill all the 210 pigeonholes with 5, and then we're going to bring in the 1 extra pigeon, the 1 extra date that will make it so that at least one of these will occur at least 6 times. And when we do that, we get 1051 dates. And I might just add some words at the end to clarify. That many dates guarantees that at least one, I'm going to tie day pair occurs on at least 6 occasions. Okay, there you go. So 1051 was what we're after. All right, now let's have a look at geometry examples. Geometry examples often involve lengths or areas, and often involves dividing up a shape into physical pigeonholes that you can actually see. So it's kind of like a good application of the pigeonhole principle. You can actually see the pigeonholes. So here we've got a square side length 2. So straight away I'm going to draw square side length 2. Okay, 9 points drawn at random inside the square. Show that it is possible for 3 of these points to form a triangle with an area less than 1 centimeter square. So I need an area less than 1 centimeter square. Okay, so this particular box here has an area of 4. So if I want something to do with an area of 1 square centimeter, I want to split this shape up so that each pigeonhole has an area of 1 square centimeter. So the most obvious way to do that is to split it so that each of these, we've got 4 1 by 1 squares. So, and then we're filling it with 9 points. So I think you can see what's going to happen. Okay, if I've got 8 points, I can put 2 in each box. But that 9th point will ensure that there is a guarantee that there must be 3 points within 1 square centimeter box. So that guarantees that we can draw a triangle. There must be a triangle with an area of less than 1 square centimeter. So that's the basic idea. Okay, so but now we just need to write it up. Okay, so I'd be explaining first to realize that for the triangle to have an area less than 1 square centimeter, the 3 points must lie in the same box with area 1 square centimeter. Okay, I'll write that down quickly. I'll pause the video. We'll come back to it. Okay, I've written down what I just said. Now let's move on. So the next thing I'd probably do is identify what's the pigeons and what's the pigeonholes. So, so the 9 points are going to be the pigeons. And the 4 1 square centimeter boxes are going to be the pigeonholes. And I do recommend for these geometry questions drawing a picture for the examiner to make it really clear what you're doing. It makes it clear. Next we're going to use the generalized pigeonhole principle. So let's write the fraction as a mixed numeral. So that's 2 and a quarter. 2 and a quarter. Okay, so we've got a 2 with a remainder of 1. So therefore, by the pigeonhole principle, at least one 1 square centimeter box has at least 3 points in it. And that doesn't fully answer the question, does it? I've just kind of quoted the pigeonhole principle. Now I'm going to make sure I've addressed the question. So show that it is possible for 3 of these points to form a triangle with area less than 1 square centimeter. So basically, I'm going to write, therefore, it is always possible for 3 of these points to form a triangle with area less than 1 square centimeter. Okay, so I've pretty much just rewritten the last sentence there. Okay. If you would like a more thorough proof of that question in terms of wording, this particular portion here, you can elaborate on it a bit and write a more full response. Okay, so this would be alternate wording using similar wording to the HSC sample solution that they've given in the past. So, okay, so this was similar to the wording of last year's HSC question 12C, the 2020 HSC. We can have at most 2 times 4, which equals 8 points without exceeding 2 points per 1 square centimeter box, but we have 9 points, so at least one 1 centimeter square box will have at least 3 points. So there will always be at least 3 points that form a triangle with area less than 1 square centimeter. So that's some alternate wording. I'll leave that up there. Okay, I prefer this wording, however, it is more to memorize. I understand. Okay, now we're going to move on to a divisibility example. This is the last question we're going to do, and this one's quite tough, but I think it's important to look at divisibility because there is often some good application questions using divisibility using Pigeonhole principle. A good tip for divisibility questions: always consider possible remainders, and you'll see that pop into this question here. So this question says that show that among any 4 changed numbers to positive integers, one can find 2 numbers so that their difference is divisible by 3. I've just written down some numbers whose difference gives an answer that is divisible by 3. So 6 and 3, 9 and 3, 10 and 4, 10 and 1. You do 11 and 5 as well. There's heaps. The key thing is that you will work out later, we'll prove it later, is that in order for 2 numbers to have a difference divisible by 3, the 2 numbers themselves must have the same remainder when divided by 3. And that'll be useful later on in the question. Okay, what I'm going to do is I'm going to type up the answer and we'll discuss it. Okay, so let's go through the solution. When a number is divided by 3, there are 3 possible remainders. You can get a remainder of 0, 1, or 2. Okay, since we have 4 positive integers, they're the 4 pigeons, and 3 possible remainders, the pigeonholes, by the pigeonhole principle, there must be at least 2 numbers with the same remainder. Now, this is where we're going to prove that 2 numbers with the same remainder is equivalent to saying that the difference of the 2 numbers is divisible by 3. We need to show that now. So we're going to write the numbers like this. n1 is going to be one of the numbers, n2 is going to be another one of the numbers. We've got it 3 times by a constant plus the remainder. So the 3 is the divisor essentially, the k1 and k2 is the quotients, and we're plussing the same remainder because both n1 and n2 have the same remainder. Okay, if you can't remember how to write, this is essentially like division of polynomial, same structure of dividing by 3. Okay, how we can write a number in terms of 3 times by something plus the remainder. And note this extra little bit here, I've said that k1 and k2 are positive integers. This e thing is an element of the positive integers, and I've put k1 to be bigger than k2. That just makes the number n1 bigger than n2. Okay, now we're going to consider their difference and show that it's divisible by 3. So we minus these 2 expressions, okay, and we do a bit of cancelling and we see that n1 minus n2 is equal to 3 times by something, and that something is going to be k1 minus k2, and because k1 and k2 are positive integers, that k1 minus k2 will also be an integer, okay, and because k1 is bigger than k2, it'll be a positive integer. So we know that the difference is divisible by 3 as k1 minus k2 is an element of the positive integers. Okay, so that's our proof. This last little bit was all about explaining why having 2 numbers with the same remainder is equivalent to having 2 numbers whose difference is divisible by 3. Okay, so we conclude, therefore among any 4 positive integers, one can find 2 numbers whose difference is divisible by 3. Alright, what I'd like you to do is to be working on the Cambridge exercise 14H. There are some tough questions there. You should be working from 8 to 18. You don't feel the need to do all of them. You might want to try all the evens or all the odds. Okay, there's a very tough question. Question 17 is an interesting one to give a go. But yeah, I'd try, just read through, and if it's a bit repetitive, skip a few, okay? Or if you like, do all the evens or all the odds, up to you. Okay, and then after you finish that, you can work straight on all the reviews. Okay, the past HSC, and the Maths and Focus review and Mastering Maths review. Okay.